Good morning. Today we shall discuss the raw materials required for manufacture of polymers. If I ask you a question, what is the basic source of polymeric raw materials or raw materials for polymers? Yes, naphtha. Is that the basic source? Crude oil again? No, I cannot accept that. The basic source is the plant kingdom. Plant kingdom is the basic source of raw materials, all sorts of raw materials, chemical compounds, because this plant kingdom acts as a energy conversion unit, solar energy conversion unit. It stores the solar energy. Now, that plants can be a major source of or the best source of this polymer raw materials. Now, this petroleum, coal, these are the fossil fuels, fossil of plant fossils. There is some geothermal conversion under high temperature and pressure. There is a lot of chemical transformations occur in plant materials. You know what is the plant material? They contain carbohydrates, cellulosic materials and lignins, compounds of carbon, hydrogen, oxygen, along with certain minerals and other atoms, elements of other atoms. The majority is the carbon, hydrogen and oxygen and little bit nitrogen. For artificial manufacture of polymers, we take these petrochemicals or the petroleum as the basic source there. You may say that yes, petroleum can be considered as the basic source, but the genesis of petroleum is from plant kingdom. Now, if you remove this lignin from woody material of plants, what we find? We get cellulose, and lignin, you can consider this lignin as a storehouse of plenty of chemical compounds. Today, large number of chemical chemicals available from world level manufacturers of chemicals and suppliers of chemicals or traders of chemicals. Majority of those chemicals are made from this lignin through pyrolysis, etc. So, if there is no, this petroleum reserve is exhausted, we have the plant system. From the plant system, we can manufacture chemicals provided we have the appropriate technology. That is different aspect. We should not discuss those things here. What I like to tell you, that majority of the polymers, artificial or synthetic polymers, those are manufactured from raw materials obtained from petroleum, and petroleum provides large number of petrochemicals. There are three major generations of petrochemicals: first generation of petrochemical, second generation of petrochemical, third generation of petrochemical. Polymer is also a petrochemical. Polymers would also be considered as a petrochemical. Okay. So, let us see we must have certain idea about these raw materials for the manufacture of these polymers. Think of polyethylene, polypropylene, polyvinyl chloride, polystyrene, polyesters, polycarbonates, phenolic resins. All these materials are obtained from this petroleum. And initially in 1970s, actually in 1970s, the first petrochemical complex was set by Indian Petrochemical Corporation of India at Vadodara for manufacture of cracking of naphtha, refining of crude oil, then cracking of naphtha. By cracking process, different types of organic chemicals were manufactured. So, it gives us a close view of different projects taken up by the IPCL that time, and here you see different chemical compounds, xylene, then polyethylene, these are the polymers actually, the polyethylene, ethylene, xylene, propylene, butadiene, benzene, and subsequently their derivatives lead to large number of petrochemical products. You can get these things from any petrochemical book. Any petrochemical book you can see. I had one book that is written, that is known as the Introduction to Petrochemicals, written by Sukumar Maiti. It is a very small book. There are many books available in our library. You can go through those things. Source of petrochemicals, the crude oil and natural gas, hydrocarbon materials, and mostly those are saturated hydrocarbons. This shows a schematic representation of petrochemical feedstocks. These are the various petrochemicals. Here you see, few are mentioned here: methane, ethane, propane, butane, propylene, butane, butene, BTX, benzene, toluene, xylene, aromatics, etc. So, these are obtained from either crude oil or natural gas. These are fractionated. From this we get LPG, liquefied petroleum gas, cooking gas, which contains propane and butane, and from crude oil we get in the form of refinery gas or liquid petroleum fraction. So, there are two fractions, gas and liquid fraction. From the gas fraction we can get this methane, ethane, propane, butane, etc. And by catalytic reforming means, you see, this is basically a straight chain hydrocarbon. This crude oil contains basically straight chain hydrocarbons, maybe say number of carbon atoms from 2 to or 3 to 10, 12 like this. From there all sorts of petrochemical compounds, all sorts of chemical compounds, organic compounds are made by some reforming process known as cracking process. What is cracking process? Cracking means breaking. Say if you have a straight chain hydrocarbon, say suppose C5 hydrocarbon, there are 5 carbon atoms, saturated C5, that means pentane or hexane or heptane, like that. Now, there the bonds present in the straight chain carbon is carbon carbon single bond and carbon hydrogen single bond. Now, when that is subjected to high energy environment, might be thermal energy or some other form of energy which should be technologically viable. So, it is better to have thermal energy in presence or absence of catalyst. Those bonds can be broken in a closed chamber. So, once those bonds are broken, that breaks by homolytic scission. You know what is homolytic scission? Suppose carbon carbon bond, if there is, it breaks, it will break into two fragments having two radicals on this carbon. This is homolytic session. Heterolytic, heterolytic, I am not showing the other bonds. So, cation or anion, this will be formed, cracked. So, this is the basic principle of cracking. So, in a mixture what happens? See, large number of molecules are there, infinite number of molecules are there. So, there are collisions as well as thermal cracking, thermal breaking into free radicals. It depends on whether it will be free radical or ionic, that depends on the nature of a catalyst which is used for such cracking operation. So, once these are formed in large number, then they can collide with each other and recombine. Okay. So, the size of this radical may not be equal to the size of this radical. One may contain 2 carbon, another may contain 3 carbon or 4 carbon, like this. So, after breaking they collide with each other and again they can form reform, or again or even they can abstract hydrogen atom from one of the other radical, that is called disproportionation reaction. So, what happens? I am showing this way. Recombination they can reform, or there are possibilities of, say, it has hydrogen, it has also hydrogen. So, this hydrogen can be abstracted. So, if this hydrogen is abstracted, then some double bond will be formed over here, unsaturated end, and other thing will be, other part will be saturated, like this. So, depending on the residual parts, hydrogen or other carbon, it can be methane or ethane or propane, and this can be ethylene, propylene, like this. All right. So, this is the things happen when they are fractionated or they are cracked, that means you are exposed to high energy environment. After that those are fractionated. So, after cracking what happens? We will have a mixture of different chemical compounds, mixture of starting compound with the product compounds. Then it needs to be separated and purified, isolated, etc., and that is done by fractionation, fractional distillation or by other means of fractionation. So, those are separated and purified, and we can get pure methane, we can get pure ethane, or we can get pure ethylene, we can get pure propylene, all right, or we may need to go for other steps where with the help of catalyst and other reagents we can convert this ethane to ethylene, like this, or benzene, or some other your monomer compounds. So, those are there. So, you can have a close view of the different chemical organic compounds available from crude oil or petroleum. Now, this shows a basic composition of natural gas. Majority is methane and then ethane. So, others are very less sometimes, and a little bit of, say, hydrogen sulfide, nitrogen. You know, the source of sulfur is there also in plant. There is a sulfur, nitrogen, phosphorus. So, those can remain in the some compounds can be there of sulfur compounds, phosphorus compounds, nitrogen compounds can be there. Compositions of natural gas available in Gujarat. Actually, this composition of natural gas varies from place to place, site to site. Composition of crude oil varies from site to site, aliphatic, aromatic mixtures, all these things, as well as different hydrocarbons present over there. I will go hurriedly, today I have to finish this, there are a large number of slides. So, here you see US natural gas consumption pattern is shown, and this is old statistics. You can get the recent or current statistics from your recent journals. Should skip these things. Classification of petrochemicals. As I told, there are first generation petrochemicals known as basic petrochemicals, second generation petrochemicals known as derivatives of first generation petrochemicals. So, from first generation petrochemicals one can get second generation petrochemicals, then third generation petrochemicals are consumer commodities or products like which we are using, say polymers, say propylene, polypropylene, polyethylene, polyvinyl chloride, polystyrene. These are third generation petrochemicals, because these are chemical compounds made from petroleum. Okay. So, second generation, look at first generation examples are methane, ethane, propane, ethylene, propylene, butylenes in the monomeric form, BTX aromatics, benzene, toluene, xylene aromatics, and second generation petrochemicals are styrene, dimethyl terephthalate or terephthalic acid, acrylonitrile, ethylene glycol, vinyl chloride, acrylic acid. These are intermediates as raw materials for plastics, rubbers, fibers, dyes, detergents, all these things. Now, you understand majority of the chemical industries in a country, they have to depend on the availability of this crude oil. If there is no sufficient crude oil, because that crude oil goes for this petrochemical manufacture as well as for what? Fuels, petrochemicals as fuels. Today, people are automobile vehicles are run by these gaseous fuels. Okay. So, then third generation petrochemicals, after obtaining these monomers from first generation petrochemicals or second generation petrochemicals, they are converted to polymers as third generation petrochemical materials. You see what one can get, distillation of crude oil. If you go to some refinery, you will see huge distilleries, distillation plants, huge structures are there, thousands of tons of your crude oil is used for cracking, distillation, separation, purification and conversion to different products. So, vacuum distillation or direct distillation fractionation. So, different fractions C5 to C8, C8 to C10, C10 to C14, C14 to C20, C20 to C24, C24 to C30, C30 to C40, and you see nature of their uses of these various fractions. Now, for road surfacing or for coke, we also depend on these petrochemicals, crude oil, high boiling fractions, those are called high boiling fractions, or residues, those are high viscous materials, they have some binding capacity, they have some adhesion properties, those are used for road surfacing, etc. So, depending on the number of carbon atoms in the hydrocarbon chain, you see their uses are different because their boiling points are different. gradually boiling point increases from top to downwards. You see some physical properties of paraffins, these are known as paraffins, methane, ethane, propane, butane. So, these are hydrocarbon. And look at the boiling points, very low temperature is required for solidifying methane, minus 182, minus 183 like this. Then when the number of carbon atoms is more than actually these are the melting point, but look at the boiling point, pentane, when the number of carbon atoms is bigger more than 4 or 5, it becomes liquid, otherwise it is gas. So, paraffin wax, its melting point actually it does not melt, showing a sharp melting point, say it is from 55 to 60, 65, 70, 55 to 70, in this range it melts, because it contains a mixture of hydrocarbons higher than C30 or something like that. So, those you can have some idea looking at these boiling points and the number of carbon atoms and carbon hydrogen ratio. This is most important thing, carbon hydrogen ratio. The calorific value or the fuel value of a hydrocarbon depends on this carbon hydrogen ratio, because this combustion is an oxidation process. Hydrocarbon reacts with oxygen forming carbon dioxide and water, as well as releasing energy. Okay. Now, if you just try to watch one phenomena, that is, there are some hydrocarbons which burn without smoke. Some hydrocarbons or oils burn with smoke or sooty flame. Sooty flame means there is some unburnt carbon as smoke that forms soot, carbon particles, that is due to the variation in ratio of the carbon to hydrogen atom. Aromatic compounds, when it is burnt, it produces sooty flame, produces soot, whereas lower hydrocarbons does not produce soot. There is complete combustion and conversion to water and carbon dioxide. Anyway, just if you go through this data, you will have some idea. It may help you, because if you want to be a polymer expert, if you want to work in polymer industry, if you want to understand the process over there, you must have some basic idea in these things. Effect of branching on boiling points of alkanes. So, here you see effect of branching is there on boiling point, effect of branching is there on the properties of polymers, that you can visualize. You will see when I shall cover the structure properties or structure property relations of polymers, you will see the effect of branching, effect of molecular weight, effect of their morphology, etc. All these things, they have profound influence on their properties. Here also the effect of branching is there on the boiling point as well as the melting point, number of branch, length of branch, etc. This is the composition of various refinery gases. Primary fractionator gas, power former tail gas, fluid catalyzed cracker tail gas, hydrocracker isomeric tail gas, steam cracker, naphtha, gas oil, hydrofiner tail gas. So, different fractions, actually these are some technical terminologies, different fractions can be available, and these are the compounds available from those different fractions. it may not be so important for you at this moment, but as a reference you can keep with you anytime it may be necessary. Availability of propane and butane from refinery. Propane volume, some statistical data is given over here. Propane, butane and source are the crude oil hydrocracking process. Hydrocracking means cracking in presence of steam. I will explain this hydrocracking process little later. What is hydrocracking, what is catalytic cracking, etc. So, from different processes we can get different percentage of hydrocarbons. Now, what is the feedstock for ethylene? That means for manufacture of ethylene, because ethylene is a base, again is a very important raw material for today's commodity polymers, polyethylene or polypropylene, etc. So, for making the ethylene, for production of ethylene monomer, what feedstocks are taken for manufacture of this ethylene? These are ethane, propane, normal butane, naphtha, gas oil, and yield of total ethylene production is percent from each of these, and total yield of ethylene production from range is given, yield of ethylene percent, total ethylene and yield of ethylene. Typical composition of the effluent gas from naphtha steam cracking. In refineries you will find naphtha cracker. What is naphtha cracker? Naphtha is taken as the feedstock, then it is subjected to thermal cracking. Cracking means breaking of hydrocarbon chains into smaller fragments, that is called thermal cracking, and that heat is supplied through steam, high pressure steam, high temperature steam. You can have steam at 100 degrees Celsius, you can have steam at 150 degrees Celsius, you can have steam at still at higher temperature, depending on the pressure of the steam. Now, that steam is mixed with this hydrocarbon gas. What happens? There is water vapor, water molecules in the vapor phase, vapor state, and hydrocarbon and thermal energy, heat energy. So, that heat energy, if it is more than the bond energy of carbon, carbon bond energy, more than the bond energy of carbon hydrogen bond energy, then those bonds will be broken. That is called cracking. Okay. Now, once, as I mentioned, once these bonds are broken, there is a possibility of major possibility of recombination to get you back the feedstock, that means the starting material. In order to prevent that, this steam is used, it acts as a diluent. You understand? It acts as a diluent. That means, if there is certain percentage of water vapor molecules are there, then when they come, when these species comes closer to collide each other to reform the starting material, that will be prevented. That means, if in this space some water molecule comes in between these two, they will be prevented to collide with each other, rather this will collide with this water vapor molecule, and temperature is high. So, it can lead to this kind of reaction with these products. This is the effect of dilution, and that is the process, and that principle has been developed to refine technology today to get the specific products of ethylene products like ethylene or propylene like this. Okay. So, typical composition of the effluent gas from naphtha steam cracking. So, you see hydrogen, some hydrogen is also produced, because hydrogen is broken, carbon hydrogen bond is broken. So, some active hydrogen atom will be produced, they may combine to form some hydrogen also. Again that may be that will react to form other compounds, that means that may add to the hydrocarbons, but some hydrogen atoms or hydrogen molecules will be there. Methane, ethylene, propylene, C4, C5 fraction and cracked naphtha, essential oil of gases, these are the various components produced during steam cracking. Now, look at this, as I was telling, look at these reactions. If you look into this thing, ethane, CH3, CH3, saturated hydrocarbon. So, thermal cracking due to homolytic scission of this bond will lead to this methyl radicals, 2 methyl radicals, highly active and energetic, highly activated state. So, this methyl radical will further collide with this ethane molecule, fresh ethane molecule, forming, that means this methyl radical will snatch one hydrogen atom from this methyl group, forming methane, as well as it will lead to an ethyl radical. This ethyl radical can give up one hydrogen from this carbon, forming a, actually this is wrong here, forming an unsaturated molecule, olefin, ethylene, producing one hydrogen radical. So, this hydrogen radical can also lead to products like this, and again it can lead to form methane. Okay. And again this hydrogen radical can combine with this thing, giving back the starting ethane molecule. So, this way you see the random process, random reaction, random collision between these hydrocarbon molecules. Here only one species is shown, ethane. If you go for cracking of natural gas, cracking of crude oil or some other feedstock, then there will be a mixture of different hydrocarbon compounds differing in number of carbon atoms in the chain. So, there will be mixture of products, but depending on the energy, that means the temperature and the presence of catalyst and all those things, pressure, temperature, pressure, catalyst, those parameters control the percentage of products, say, so this is, if this is the most desired product, the technologies would be such that maximum percentage of this will be produced along with minimum percentage of other products. Then the product mixture, this is the product mixture, should be subjected to fractionation, isolation, separation, purification. You see, cracking of ethane, you look at the temperature, cracking of ethane yields about 97% ethylene. The cracking parameters used are very high temperature. This is the pressure. Ethane steam ratio is 2.5 to 6. The optimum condition is 60% conversion of ethane per pass. That may be tubular reactor is circulating, and this is connected to separator also, separator fractionator. So, per one pass it produces 60% ethane, conversion of ethane to ethylene. small amounts of carbon monoxide and carbon dioxide are generally formed. That is also possible. So, you see product composition from this cracker. You can take time later and go through in detail. Catalytic cracking. Now, this if you go to once again to the previous slide, this temperature is very high. This high temperature and pressure may not be economically suitable, economically acceptable. That means, the product of this cracker, the cost of the products of this cracker will be high. If the cost of those products are high, then that means the cost of raw materials for polymer is high. Okay. So, your monomer and polymer from that monomer cannot compete in the market. Today, entire globe is open, there is open market. Now, in India there are few polymer manufacturer, petrochemical industries, they are manufacturing these polymers. Now, if some other manufacturer from other country, they supply polymer to India, then in the Indian market, if the imported product, imported polymer is available cheaper, then our petrochemical industries should be shut down, they cannot make profit. So, there is huge competition today because of very efficient catalysts developed for such cracking operations, refining operations. That means, your production cost of these raw materials for polymer should be as minimum as possible. Now, if such high temperature and pressure is required for manufacture of those monomeric raw materials, then you cannot compete in the market with the cost of polymer with other manufacturers. So, this is the basic reason. That is why, if some catalyst, you know, the presence of a catalyst can decrease the activation energy of any reaction, of any process. So, energy consumption, thermal energy consumption during the production of these raw materials or during the production of these polymers is minimized, then there is huge saving of money. So, cost of the raw material will be lower and that can find competition in the market. Your product will be sold in the market, will be taken by the consumers, customers. So, that is why the catalysts are used for this catalytic cracking purpose, and the cracking temperature is usually 450 to 520 degrees Celsius. Today, I do not know what is the temperature, modern, this is little old information, just to give you some idea. Since I had these materials, I am showing you, there are recent books, recent literatures available in the library, please go through it. There you will find the conditions of this cracking process, temperature, pressure and the nature of catalysts, please go through those things. Reaction variables as the optimum condition for naphtha steam cracking. These steam cracking variables I have already shown to you, and look at the reaction scheme in catalytic cracking. In the thermal cracking process, you saw the homolytic scission of this carbon-carbon bonds leading to smaller fragments of monomers or other smaller hydrocarbons. Here you see, in presence of catalyst, this cracking process undergoes by ionic means, and that leads to these monomers like propylene or ethylene or other monomers. The product mixture obtained from a catalytic cracker depends on a number of variables, namely nature of feedstock, nature of catalyst, cracking conditions, etc. The separation and purification of propylene is same as for ethylene. Again, there is huge cost involved in separation of one particular product from a mixture of different hydrocarbons. How many of you have performed distillation of solvent in the laboratory? What apparatus is used? What setup? What apparatus is there in that distillation setup? Soxhlate is not a distillation setup. Soxhlate is a setup used for, you can say, extraction. Soxhlate is not a distillation setup. What is the principle of distillation? You take a solvent in a container, supply heat, it will start boiling, vapors will be produced, and at a particular pressure it will boil at a constant temperature. So, due to boiling of that liquid, it produces vapor molecules, and those vapor molecules need to be condensed. So, you must have a still, distillation still or a container where you have taken the liquid, that still is connected to a condenser. So, vapor will be generated by supplying heat from the bottom of the still or container. The vapor will try to go out and pass through the condenser, where some coolant is being continuously passed. That coolant may be cold water, chilled water, or some gas also, cold gas, cold oil. So, those vapor molecules will be condensed to form a liquid. That means, that is a fraction containing that is the pure form of one particular fraction, which starts boiling at one fixed temperature and continues till the last trace of that compound is removed from the distillation still. That is the distillation process. Now, here many things are there, those are chemical engineering aspects and unit operations. It is a very simple setup. I have told you, simple distillation setup that contains a container connected to a condenser and a receiver. In the receiver, that distillate is collected as a condensate. Okay. Now, the efficiency of distillation, efficiency of distillation means at minimum energy consumption, you have to separate or you have to distill a component in a pure form. Now, if that vapor is condensed properly, then distillation will be faster. Otherwise, there will be it will go back to the still and it will be collected in the same container rather than getting as a distillate. So, for that it needs high surface area, high condensing surface. So, for those different types of different designs of condenser are available. Anyway, those who will be going for synthesis of chemical compounds or polymer materials, they may need this kind of distillation. And again the distillation can be done at a lower temperature than its normal boiling temperature, because the there is a possibility of degradation, thermal decomposition of the compound which you, of the liquid, of the solvent which you want to distill or separate by fractionate. So, distillation is a kind of fractionating process technique, fractionating and purification technique, by which you can separate one particular pure component from a mixture. There are other techniques also, as he told, Soxhlate, that is used for also separation by extraction, liquid extraction, solid liquid extraction, all these things. So, there are various techniques or unit operations found in or followed in chemical engineering. Those are necessary for our purpose also here. A typical composition of the effluent gas from naphtha cracking, you see, of course, catalytic cracking process is there, you read. Now, simplified flow plan of naphtha steam cracking process. Stephen, you are not getting, Stephen, are you getting interest? Because you are from different subject, I know. Any of you feeling uneasy? Feeling uneasy? Why? No, it is not that you have to just remember everything from this I am showing. For your some exposure, for some exposure I am showing these things to you. It is necessary, it will be necessary in the next subsequent lectures, you will see. So, some reference will be there. So, I am showing for your information. You see, the naphtha steam cracker is a reactor where cracking operation is done. Then this is fractionator, I was telling you. Then wash tower, again this is a kind of purifier. Then it is dryer, then demethanizer, that means some methane is removed. Okay. And again from here it comes to the demethanizer, depropanizer, acetylene hydrogenator. That means you see, in a process after cracking there are large number of, or say few number, say 5 or 6 compound mixers are there, mixture is there in the product stream. From there you have to isolate one specific product. How to get? These are the various techniques. Say methane is removed, ethane is removed. If you want say ethylene, methane is removed, ethane is removed. Then if there is some acetylene, actually by hydrogenation of acetylene is hydrogenated. So, various units are there. So, and this product stream is passed through all those things, and ultimately you can get propylene, ethylene, and this is something wrong with this will be propane. The propane, some mistake is there, this will be propane. So, some propane, propylene and ethylene you can get. The schematic information. We started with naphtha and steam, feedstock, some units, it passes through some units, and ultimately you get these products, and these are the basic raw material, these are the raw materials for making polymers. Again, if you want to make ethylene from ethanol, you can go for dehydration technique. This is the specification of polymer grade ethylene. Polymer grade ethylene means ethylene which is used for making manufacturing polyethylene. 99.9% purity of ethylene is there, and the rest of the things are there, but in very low concentration, 1 parts per million, 10 parts per million or 250 parts per million. Actually, these influence the final properties of the polymer. Market. Petrochemical, different petrochemicals from ethylene, see, different petrochemical from ethylene through derivatization, through derivative formation. You can say these are chemical process industries, chemical process units, various chemical process units leads to different products if the source is ethylene. So, these are also raw materials. If you have ethylene, then from ethylene you can get other raw materials, means in the form of polymers through some chemical transformations, chemical reactions. You can see, you can get styrene, you can get formaldehyde, you can get vinyl chloride, you can get ethylene diamine. So, you have the ethylene. If you have ethylene, pure ethylene at low cost, you can have these plenty of raw materials. Product profile of catalytic cracker. Propylene, you see, propylene is 4.5, is not very high. You can have gasoline, residue and coke. Why the cost of polymer is so high? 1 kg polymer. No, what is the cost of polyethylene today? Yes, please. Pradipta. So, 70 to 80 rupees 1 kilogram. If you go to market for buying one bucket, polyethylene bucket, how much they take? Say 10 liter bucket. Have you not purchased? How much it costs? 50? No, it is more than 50. How much you paid? Bit louder. 65, 70, 80 rupees, 100 rupees. Yes, you are right, 100 rupees. It depends on the manufacturer, company, qualities, etc. So, that is not 1 kg, around 250 grams, 250 grams or 500 grams or say 300 or 400 grams. So, if the raw material cost is, your polymer cost is, if that polymer 1 kg polymer is available in 75 rupees, how come that 300 gram bucket takes 80 rupees or 100 rupees from you? They are making huge profit. Are they making huge profit? No. You have to add the process cost for manufacturing that bucket. That may not be again so high. See, the 300 gram polymers, how much is the cost? 20 rupees, 25 rupees, like that, 20 to 25 rupees. So, add process cost to it, another 15 rupees or 20 rupees. So, huge margin is there, huge profit is there. So, my suggestion to you, all of you, instead of going for job, hunting for job, okay, you start one entrepreneurship of manufacturing buckets and supply to these hostels, where you can make a profit of say 30 to 40 rupees per bucket, mugs, tubs, and even your monofilament, polyethylene polypropylene monofilament for making mosquito nets. How many of you have mosquito nets in your hostel? Only one. Be careful, huge mosquitoes are there. So, you should buy, and that mosquito net is made of nylon. Nylon nets you are using. Are you using nylon nets? Nylon nets. What is the cost? What is the size? 3 feet by 3 by 5.5 or 6 feet. 3 by 6 is they are taking 200 rupees. It is made of polyethylene monofilament, not nylon. Nylon net will be much expensive than this one. So, you manufacture polyethylene monofilament. So, do not ask for a job. Okay. There are many other outlets of manufacturing plastic or polymeric products. You can make capital investment. Yes, now he has come. Who has told capital investment? Capital investment. Okay, your friend is quite rich person. There are some friends. Stephen is there. Stephen is quite rich, so he can supply money. Yes.
Imported plastic will be more costly.
Imported plastic. Why you are going for imported plastic? Better quality? Not necessary. It is always the imported plastic, imported material are better quality than the manufactured in India. Anyway, so these are, I have given you a brief picture of these raw materials for this polymer manufacture. Now, if you have any question, queries, you please ask me. Any queries? After reading, that means, am I to accept that you have wasted your time in this class? Then why after reading? Why not immediately? Hammer the iron while it is hot. Is not it correct? I will forget, you will also forget. Then you should immediately ask in the class, sir, what is this, what is that? You have not explained that part clearly. Next day we shall start polymer synthesis.